Welcome to Calculus Section 7.3, Day 2. In this video, you will learn how to apply the washer and disks methods for finding the volume of revolution when the line of revolution is the y-axis or some other vertical line. You will also learn to find the volume of solids that have a base defined by curves in the xy coordinate plane and a height defined by some kind of repeated geometric relationship. Last video, you learned how to calculate the volume of revolution by using the disk or washer methods. Using these methods, you find a rectangle of some fixed width, we'll call it delta x, whose height is determined by the distance between the two curves in the xy plane, or in the case of the disk method, the distance between a horizontal line of revolution and the function value at x. You then revolve that rectangular region around the line of revolution to form a disk or washer. We then repeat this for the next value of x, incremented at delta x, which is here, and make that rotation. And we repeat that for all of the rectangles that form this region, and we sum them as we go. And once we've added all those rings up, we have a pretty decent approximation for the volume of this object. Now, you may have noticed, when doing this, that the smaller the rectangles are to begin with, we might start with this many, the more accurate of an approximation for the volume of that shape we have, because the original shape we're approximating is also much closer. This is sort of like the Riemann sum idea. In this video, we will extend this technique to functions of y revolved around a vertical axis. When revolving around a vertical line, very little changes in your technique, really. You may notice that I just took that previous image and flipped it around, so my axes are labeled wrong, and I do apologize for that. This says this is the y-axis, and this says this is the x-axis. Pretend it's not labeled like that. Pretend it's labeled normally, that this is the x-axis and that's the y-axis. And so now our rectangles are lying flat on their side. So our calculations, really, when we do this rotation, should be nearly identical to the calculations that we made before. The difference, of course, is that we're rotating it around this vertical axis. But otherwise, it's really exactly the same process. There are a couple notable differences, however. The first is that the width of our washer, or our disk in the case of the disk method, is now going to be based on a change in y values, or some delta y, as opposed to delta x when we revolved it around a horizontal line. And the second is that our width of our rectangle is now going to be based on the difference between this curve, this bottom curve, and this top curve. But lengthwise, that's going to be the difference in functions of y as opposed to functions of x. So we need to have our functions in terms of y instead of x. But that's actually fortunate, because if you remember, the method we used to find the volumes of revolution last time was to integrate, right, with respect to x. And in this case, we'll be integrating with respect to y because we'll have functions in terms of y. And we'll have differences, or delta y's, or dy's. So that's also in terms of y. So we'll be all set up to integrate with respect to y. Finally, because we're going to be starting way down here and working our way up, the boundaries of our integration when we do this process are going to be in terms of y as well. Let's see if we can calculate the volume of the solid formed by the rotation of this shape around the y-axis. The top curve is x equals y squared, and the bottom curve is x equals the square root of y. Notice how that's flipped from the shapes we'd ordinarily expect from those functions, but that's because we've flipped x and y. So the volume of the washer is pi r1 squared h minus pi r2 squared h. where R1 is the bigger radius of the washer, going out to here, and R2 is the radius of the smaller disk that we're going to take out of the center of that washer. So which functions do these match up to? Well, R1 has to go out wider, so that's going to connect to the bottom curve, the square root of y, and R2 has to go to the smaller disk that we're taking out. That has to go to the top curve, x equals y squared. This has to be the case because we're looking for a positive volume, so we're going to want to take the bigger radius and subtract the smaller radius. So therefore, what we should be able to do is write the volume of that washer, that particular disk, as pi times, here's our radius, the square root of y, and I've subscripted it with alpha 1 just to show that we're talking about this first disk here, or this first washer here, and then times h. So we're going to square that. That's our radius squared. And then here's subtracting pi y squared, again at alpha 1, squared times h. Note that we could also say that h here in this equation is really the change in y as we look at successive rectangles. So we could really call that delta y. And so here I've simplified things a little bit. I've said the square root of y alpha 1 squared is just y alpha 1 squared. And I've said y alpha 1 squared squared is y alpha 1 to the 4th. And I've replaced h with delta y. So our equation is looking a little bit nicer. We can see that this relationship is going to remain for any washer that we look at. Like, let's say we're not looking at alpha 1 down at the bottom here as a y value, but we're looking at y alpha k, some y value farther up the y-axis. Well, that generates a bigger washer. But the idea is the same, right? We look at the curve generated by the square root of y out here and get this value from it as a radius. And then we look at our inner curve generated by the y squared curve to get this inner radius. So the boundaries of this region in the xy plane are y equals 0 and y equals 1. And we can actually verify this algebraically if we want, but we won't do that here. We can notice that this is the same idea as Riemann sums. In other words, that if we increase the number of rectangles and decrease their width, that this results in finer and finer washers, with the limiting result summing to a perfect calculation of the volume of the solid. So, therefore, we can really rewrite this. I'll factor out a pi. I'll replace the delta y with dy. And I'll use an integral instead to sum up all these areas. And now I don't really need my subscripts anymore because I'm varying across all of y within these boundaries 0 and 1. So I'm just going to call it y minus y to the 4th. Let's perform this calculation. So volume is equal to pi times the integral from 0 to 1 of y minus y to the 4th dy. This is just using the power rule in reverse. So I can split this into two separate integrals, and that will make my life a bit easier. And then again, using the power rule in reverse, I can come up with volume being this guy here. I'm not going to read it out to you, but I'll give you a second to copy this down. And we're going to evaluate this from y equals 0 to y equals 1. When we do that, I'll just sub 1 in, and then I'll subtract that exact same integral evaluated at 0. And that really just simplifies down to 1/2 pi minus 1/5 pi, which is, if we simplify the fractions, 3/10 pi. And of course remember that your units will be in cubic whatever, depending on what the units of the original problem was. Let's look at the second kind of volume problem in section 7.3. This involves a base of a certain shape. In this case, a parabola, y equals x squared, bounded by the line y equals 4 and the lines x equals negative 2 and x equals positive 2. And then this base is extended three-dimensionally by using cross-sections that are all squares. And these squares have a side length that is the distance between y equals 4 and y equals x squared. In other words, these side lengths are generated by the shape of the base. And so we can generate a solid by moving those squares over intervals in x until we produce an entire solid. Let's take a look at what that looks like if we have some kind of permanence to the shapes. Okay, and there's the solid that we would generate using squares, and we can rotate this around and take a look at it. You can see a lot of the properties of the paraboloid are retained. And we can repeat this idea with really any kind of cross-sectional shape. We could use triangles, for instance, and generate the solid that way. Or semicircles. And so on. So let's actually calculate the volume of one of these solids. We can actually use the one that we just looked at. And that's the one that's got this base that is the curve y equals x squared on the bottom and y equals 4 along the top. And notice that we form an artificial sort of boundary just by their intersection at the point x equals 2, y equals 4, and at the point x equals negative 2, y equals 4. So how can we do this? Well, we're sort of going to do the same thing we did last time. We're just going to take these squares, and we're going to find the volume of each of the rectangular solids they make, and we're going to add all those volumes up. So the most important question when we're dealing with problems like this is, what is the volume of one of those little rectangular solids? Well, it's a rectangular solid, and the face of the rectangle is a square. We've already said that because we've got a cross-section that's a square. So that means we're going to have s squared, where s is the side length, times h, right? And where h is the width, right here, of the rectangular solid. Okay, so that leaves us with a couple things to deal with. What is s squared in the context of, y and x, the variables we're actually dealing with? And what is h in terms of those variables? So h is really just our delta x. It's the change in x from here to here. S is a little bit trickier, but it's the distance between the line y equals 4 and the curve y equals x squared. And so we can think of s as being 4 minus x squared. So we can rewrite this as 4 minus x squared, that's s, squared, times h. And again, h is delta x. And we could go into a lot more detail about this, but let's just sort of skip to the chase. We're going to do the same thing we did. We're going to sum up all of those possible squares that we can form in this thing. And we're going to take the width of those squares and make it go to 0. And we're going to take the number of squares and make it go to infinity. So we're basically taking the limit of it. And again, it's that Riemann sum idea. That means we're going to be integrating. So by integrating, we find that our volume is just going to be the integral from negative 2 to 2. Those are our boundaries, again. Of 4 minus x squared, that's the side length, squared, dx. That's our really tiny width. I think solving this really shouldn't be too much of a problem. You could make a substitution, I suppose. Or you could actually just FOIL this out and break it up into your own separate integrals, and that will work just fine. So I hope that after watching this video, you feel confident that you can find the volume of revolution for a solid that was formed by rotation around a vertical line. Or you can find the volume of a solid formed by geometric cross-sections projecting from a functionally defined base. Really, these are the exact same idea. You're just integrating over these cross-sectional chunks. And in one case, the cross-sectional chunks are washers or disks. And in the other case, the cross-sectional chunks are squares or circles or equilateral triangles or any sort of shape that you want to talk about. All right, well, I'll see you in class then.